Hi students, welcome back to another coding problem. Today we are going to solve lowest common ancestor of a binary search tree. Let's go to the problem statement first. So the problem statement says we are given a binary search tree. Binary search tree is nothing but a binary tree with order. So left child is always less than root, which is less than right. Okay, and binary, it's binary, which means it has only two children. Okay, we have to so given a tree like that, which is an ordered binary tree, we have to find the lowest common ancestor. Okay, how is lowest common ancestor defined? The definition is that it is the first common node of the given two nodes. Okay, and what are the constraints we have? It is always given that P is never equal to Q, and P and Q will always exist in the binary search tree. So if we note these constraints, we can eliminate lot of corner cases since it's already guaranteed. So let's go over the solution for this with an example. Okay, let's say the given input is 6280479 and so on, which in a tree form would be represented like this. So we are looking for the lowest common ancestor of, let's say, two nodes 2 and 8. So if you look at the tree representation of it, it's very clear that the uh, common ancestor, the lowest common ancestor of it is 6. Okay. How do we find it programmatically? If you observe, we know that the left side of the tree is always less than root, which is less than right side, right? So for these two nodes, to have a common ancestor, they have to lie on the either side of the tree. So when we find one such point, that is enough, and that will be our lowest common ancestor. For example, for let's say we take a different example. Let's say we take 0 and 5. Okay, for 0 and 5, when we start at root of the tree, the first thing we will do is we will check where 0 and 5 are. Okay, 0 and 5 are on the same side of the tree. Both are less than 6, which is why they are on the same side of the tree, which means our solution should lie in the left side of the tree. So we will now recursively go to the left side of the tree. Who is on the left of root? 2. So we will now check for this tree. Okay. So in this tree, in this subtree, which is the left of root, again we will check where 0 and 5 are. Are they on the both? Are they both on the same side of the tree? If you see clearly, they are not on the same side, which means 2 is our answer. Similarly, if you take another example, let's say this time we take 3 and 5. Okay. So when we start at root, 3 and 5 are both on the left side of the tree, which is on this side. So we take the tree with root 2. Then 3 and 5 are on the right of this subtree. So we take the right side of the tree, which is tree with root 4. Then when we compare at 4, 3 and 5 are not on the same side. They are on the either side of the tree. So that is our answer. Okay. Now let's check a different case where the P and Q are children of each other, which is, let's see if we are looking for 4 and 5. Okay. In this case again, initially when you are looking at root, both are on the left side. So you look for a tree with root 2. Then when you are looking at 2, 4 and 5 both are on the right side. Then you look for the tree on the right of the tree, right of the root, which is tree with root 4. Okay. When we are at 4, okay, 4 is one of our elements. So we just return it. Okay. So obviously when we are checking the same, we can check the same condition, right? Like whether 4 is on the right of the tree or left of the tree, whether 5 is on the right of the tree or left of the tree, and they are not, so this is the answer. So this one, when they are having the same tree, this will work out because here it clearly says node can be a descendant of itself. So 4 is a descendant of itself, which is why this is correct. Okay, so let's write code for this. So the first condition, so the two conditions we have to check are whether the nodes are on the left side of the tree or on the right side of the tree. So let's check for right side first. Let's say p dot val, which is, we are already given a tree node here. If you see, it has value left and right. So what we are given is root. So P and Q are two nodes in that root. P dot val will give its value and the values are unique. So there is no need to worry about that. Okay. So what we have to check whether they are on the right side of the tree. P dot val should be greater than root dot val. This will work because it's a binary search tree. And Q dot val should be greater than root dot val. So what does this mean, this condition? Both P and Q are on the right side of the tree. So what do? We recursively look for right side of the tree. Ancestor, instead of root, we can now go to the right of it. What we are looking for are still same P and Q. Okay. Now if this is not true, what else can happen? P can be on the both of them can be on the left side. P dot val is less than root dot val and Q dot val is less than root dot val. When this happens, what should we do? We should look on the left of the tree. Okay. Now if nothing happens, both P and Q are not on the left, both P and Q are not on the right. That means P is on one side, Q is on one side. Or either P or Q, one of them is the root. In that case, we just return the root because that is our answer. Okay. So this is our simple recursive solution. Let's run this and see. What happened? Okay, we have a typo here. Okay, let's submit this. Yeah, so our solution is accepted. Okay, so what is the time complexity of this? So in worst case, we have to traverse the entire tree. If the tree has n nodes, we have to go through all the nodes to find the complete structure. So it is order of n. Similarly, space complexity, though we are not using anything, since it is a recursive function, that call stack trace of doing n calls would be order of n. Okay, so this is our simple recursive solution. Hope you have enjoyed it. Please leave any comment if you have any questions. Do like, share and subscribe. As always, keep practicing. Happy coding!